Hi everyone, today we will be looking at how to form and name ionic compounds and how to name molecular compounds. Forming molecular compounds can be a bit complicated, so that will be discussed in later videos when we talk about bonding. First of all, let's talk about molecular compounds. When looking at molecular compounds, it's important to recognize the elemental molecular compounds that form in nature. There are 7 of these elements that form molecules with 2 atoms: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Notice that on the periodic table itself, it forms a 7 at the right side plus hydrogen on the left side. You have to know this for later when we start incorporating more math and stoichiometry with our chemistry, because in real life, these elements all form duple forms in the natural state. So you will never see oxygen, just always O2. Now, let's talk about molecular and empirical formulas. These formulas only apply to the molecular compounds, aka molecules. Empirical formulas can be seen as a simplified version of molecular formulas. For example, you've probably seen hydrogen peroxide, H2O2. H2O2 is a molecular formula, but as you can see, this compound's numbers can be reduced. Both the 2's can be reduced to 1's, so we can say that the empirical formula of H2O2 is simply HO. Let's try one more, and I encourage you to try this one on your own. Let's take acetylene, whose molecular formula is C2H4. What's the empirical formula? If you guessed that the empirical formula was CH2, you'd be correct. Note that you can always convert from molecular formula to empirical formula, but if you're only given the empirical formula, the molecular formula could be infinite possibilities. Now, let's talk about naming some basic molecular compounds. When you think molecular compounds, you should think nonmetals, because molecular compounds are made primarily of these nonmetals. When naming compounds like these, you use Greek prefixes: mono, di, tri, tetra, penta, hexa, hepta, octo, nona, and deca. You probably won't need to go higher. Notice that tetra is 4, not quad or something like that. Here's the rule for binary molecular compounds. On the first element, you use the prefix unless it's just 1. If it's just 1, you skip the mono and just say the element itself. And on the second element, you use the prefixes no matter what and change the ending of the element to "ide." For example, CO2 is carbon dioxide, and CO is just carbon monoxide. You try one. What is N2O4? N2O4 is dinitrogen tetroxide. Alright, now let's talk about ionic compounds. Ions happen when an atom loses or gains an electron and therefore gains or loses a charge. In the previous video, you may recall that I talked about certain groups on the periodic table forming certain charges. Let's quickly review those charges and add a few more. If you remember, the alkali metals form +1, the alkaline earth metals form +2, the halogens form -1, and the chalcogens form -2. Nitrogen also forms -3 and aluminum forms +3. Some other charges you absolutely must know are silver, which forms a +1 charge, zinc, which forms a +2 charge, and cadmium, which similarly forms a +2 charge. These are all no exceptions. First, we will talk about forming compounds with these basic elements with which we know the definite charge. To name these compounds, you simply change the ending of the negative ion to "ide." Whenever you form an ionic compound, one atom gives an electron or multiple electrons to other atoms. So overall, the charges must be balanced because these compounds are neutral. Let's look at our favorite friend, table salt, aka sodium chloride. We know that sodium forms a +1 charge, which means it loses 1 electron. We know that chlorine forms a -1 charge, which means it gains 1 electron. Since the -1 charge and the +1 charge cancel out, the formula would be NaCl. Now, let's try a more complicated one. How about the element that forms between barium, an alkaline earth metal, and nitrogen, an element that forms a -3 charge? This one may seem a little bit complicated, but I have a simple trick for it. When you have elements that don't reduce well, such as this compound where we have a 3 and a 2, simply put the charges of the ion at the top, as you see here, and crisscross them downwards, switching them into coefficients. Sometimes you may need to reduce, but not here. As you can see, we now have barium nitride, Ba3N2. Now, let's talk about the transition metals, the large majority of the periodic table. These elements can form multiple charges, so whenever we name these compounds, we need to make sure we include some designation of their charge. We used Greek prefixes before, but now we're using Roman numerals. Whenever we name a compound with a transition metal at the beginning, in between the positive ion name and the negative ion name, you must put parentheses with the Roman numeral in them designating the charge. For example, if you have an ionic compound that's FeO, we know that oxygen always forms -2 charges, so to balance it out, we have 1 iron. So that iron must also have a +2 charge. Rather than just calling this iron oxide, we must call it iron 2 oxide, and don't forget those parentheses. Why don't you try 2 examples? First of all, name this compound CuI. We know that iodine has a -1 charge, and to balance it out, 1 copper must have a +1 charge, so this compound is copper 1 iodide. Now, try writing this compound out, vanadium 5 oxide. Don't forget that crisscross reduce trick I showed you. We put the +5 at the top next to vanadium and the -2 next to oxygen. We switch them up and we get V2O5, vanadium 5 oxide. The final thing we must discuss with ionic compounds are the polyatomic ions and the hydration states. Before, we were discussing ionic compounds with just 2 atoms, an anion and a cation, which are also negative and positive, respectively. However, ions with more than 1 atom are called polyatomic ions. You've probably heard of ammonium used in cleaners. Ammonium is a polyatomic ion with the formula of NH4+. It can be used in replacement of a metal. For example, ammonium chloride, NH4Cl. If the polyatomic ion is negative, which is usually the case, do not under any circumstances change the ending to "ide." A list of polyatomic ions will be found in the description of this video, and if you are taking the AP chemistry course, it is important that you know them all, or plug them into your calculator. We also have hydration states. With some compounds, you may see a dot after the anion connecting it to water. This just means that there are water surrounding the ionic compound. For example, a common one to see is CuSO4.5H2O. To name these compounds, you must attach one of the aforementioned Greek prefixes to the suffix hydrate. Try naming this compound. The name of this compound is copper 2-sulfate pentahydrate. When doing calculations with the atomic mass, you must take into account the waters attached. Well, that's all I have for you guys today. I hope you guys enjoyed learning about naming and forming compounds, and if you guys have any questions at all, please let me know in the comments. I know this video was quite informationally dense, but this topic is one of the foundations of modern chemistry and is essential to know and understand. I know I did not cover acids in this video, but a shorter video discussing acids will be coming soon. Next week, we'll be discussing chemical reactions and the mole, my favorite topic. I'll see y'all in the next one.